Alright, so begins lecture 8 again. As you can see, I was started and then I got a phone call. Let me just, rather than writing out again, talk through it here. So suppose you have vector v with basis v1 through vn. Alright, then the dual space to v, the set of linear maps from v to r, has basis v upper 1 through v upper n, the standard linear algebra, right? And the dual basis in particular is defined so that the v upper I acting on v lower j is Kronecker delta ij. Well, that defines the values of the so-called dual basis on the basis, right? And so you can extend that linearly, and that uniquely defines the dual basis, this condition right here, because it's giving you the values of these linear functions on a basis. All right, so the idea of a coframe is to do this at each point for a given frame. So at each point in R3, we take the frame E1, E2, and E3, and we can create, well, I say each point, I should say, really for this sentence, it's all of R3, all right? So, but at each point, right, E1P, E2P, E3P, that's a basis for the tangent space at P. Well, the dual basis in the sense of classical linear algebra, the set of linear functionals on the cotangent space, or the dual space to the tangent space, is denoted theta 1 of P, theta 2 of P, theta 3 of P, all right? And you do this at each point, and the assignment of P goes to theta j of P for j equals to 1, 2, 3. That defines a coframe. You might say, well, why don't you call it a dual frame? I don't know. People call it coframes. I'm sticking with it. So it's a coframe. Theta 1, theta 2, theta 3. It's a set of differential one forms, which are, in this sense, dual to the frame field, which we're given. So, just to recap, E1, E2, E3, a frame on R3. We say a set of differential one forms, theta 1, theta 2, theta 3 on R3 is a coframe. If we have this condition, if the theta I acting on EJ is Kronecker delta ij. In other words, it's either 1 if they match, if I is equal to j, or it's 0 otherwise. And that's for all I and j in the set of natural numbers going from 1, 2, 3. Sorry, n sub 3 is my my notation for 1, 2, 3. Sometimes I like to write that. Fine, whatever. So, of course, you want to know, how do you... Well, coframe, then, is going to give you a natural way to express, things that are differential one forms, or if we took wedge products, even differential p forms, right? So, let's see here. For example, if I have, well, I guess I need to get the point of, if theta 1, theta 2, theta 3 are one forms, and this is for a given frame, E1, E2, E3, then we also have dx, dy, dz, right, as one forms. And so a notation for a set of all one forms is this, lambda 1, R3, okay? And, I'd like to say that this coframe and this set of differentials, all right, they're both giving you, we could say, quote-unquote, a basis for this, but, I should be careful. It's not a linear algebraic basis. The coefficients are actually functions. So there's a natural question, how are these thetas related to the dx, dy, dz, right? We could think about that. So how are these related, right? So for example, theta 1 should be equal to a dx plus b dy plus c dz for some triple of functions abc. Let's see here. How do we work with the differentials? Well, remember the quintessential thing was that dxi acting on uj was the same as uj acting on the function xi, right? Which is really just partial xi, partial xj, which we know is Kronecker delta ij, right? Oh, hey, look at that. This shows you what? by the way? What did we just discover in the in this larger discussion here? We just discovered something, didn't we? This shows what? This shows the frame, the Cartesian coordinate frame, u1, u2, u3, has coframe dx, dy, dz. Or if you like, dx1, dx2, dx3. I like that a little bit better in some sense here. We use both those notations. So there's a coframe. Differentials form a coframe on R3. But you know, how is the coframe related to how is theta 1 related to dx, dy, dz specifically? Well, let's think about that. If we take theta 1, right, and I take theta 1 and I act on theta 1 on u1, what's that give me? Well, that gives me a dx on u1, right, plus b dy on u1, excuse me, plus c dz on u1. Well, this is 0. This is 0. This is 1. So theta 1 on u1 is equal to a, and likewise, go through the same argument with theta 2 and theta 3, and you'll get theta 2 on u2 is, well, if I use the same ABC notation, which would be kind of weird, but anyway, that would be like B. I'll put some quotes on that. And theta 3 on u3 would be like C. Or in particular, I mean that we get the result theta, how can I write this? Let's see here. Oh, theta. Oh, I'm sorry. I'm being silly. I should really put one, all three spots on. Let me focus here. What am I doing? Sorry, guys. There. So theta 1 on u2 would be B. I think you can agree with that. Theta 1 on u3 would be C, because this and this would be 0. Whereas, so in the first case, we get the last two 0. When theta 1 eats u2, it makes the first and the third thing 0. When theta 1 eats u3, it makes the first two 0 and leaves the last one being 1. So in total, what we see is that theta 1 is equal to what? It's equal to theta 1 u1 dx, plus theta 1 u2 dy, plus theta 1 u3 dz. And so there you go. It's a neat little formula for how to get the coefficients of the differential one form theta 1 with respect to the Cartesian coframe, which you could call these the Cartesian coframe, right? If you like. So let me try to say something a little bit more systematic here, because I kind of changed paths mid-example there. That was bad. Sorry about that. Proposition 2.7.3 states the following. This is the components of a vector field y, which would be a vector field in R3, and a one form alpha, which we could use lambda 1 R3. I should have systematically introduced that notation earlier, but I have not yet, but I will anyway. Components of a vector field and a differential one form with respect to frame E1, E2, E3 and coframe theta 1, theta 2, theta 3. So y can be written as a sum j equals 1 to 3 of theta upper j acting on y, ej, and the differential one form we can write as a sum j equals 1 to 3. I think Matthew's discovered I'm in here. Alpha of ej, theta j. All right, so that's the proposition. The proof of it is really pretty elementary stuff, but I think it's important to go through because this is so fundamental to so many calculations we do. So proof. All right. First of all, let me just show you what happens if I have. First of all, I should say E1, E2, E3 forms a frame, right? Hence basis for TP R3 at each P in R3. Hence, there exist functions, let's say C1, C2, C3, for which y is equal to C1, E1 plus C2, E2 plus C3, E3. All right. Now, okay, great. If I then, so that's, you know, by assumption of the basis, right? So then if I let theta j, right, act on y, what do I get? I get theta j acting on C1, E1 plus C2, E2. Maybe the room next to the washing room was not the best choice for putting this lecture together. Oh well. Sorry. I will eventually be driven to school. C1, E1, C2, E2, C3, E3, like that. But again, this is done pointwise, so I can pull the functions out. And you see what we're left with. C1, theta j E1, C2, theta j E2. Sorry, entirely too much writing here. Plus C3, theta j E3. I should really have used the summation. And you see that each one of these is going to be 0 except for the one where the index matches j. So what we're left with, of course, is just cj, because we have theta j ei. It's Kronecker delta ij, right? So it just leaves you that one term with I equals to j. And you get cj. So therefore, y, you can see, is equal to a sum, j equals 1 to 3, of theta j acting on y, because that, after all, is the cj times ej. So there's part of the proposition right there, right? So likewise, this time I'll use summation. We have alpha is equal to a sum, j equals 1 to 3 of some functions, let's say b sub j, times theta upper j, because, you know, as theta j is coframe, it provides a basis at each point, right? But you can evaluate alpha on ei, right, and use the linearity of the one form at each point. It's a covector, right? So I can pull the summation out by this distributivity, pull the functions evaluated at a point, which are just scalars at each point, bj, and then I have ei, theta j, upper j, acting on ei, all right? And, oh, but that's Kronecker delta ij. And so we're just left with b sub I. So therefore, alpha is equal to a sum, j equals 1 to 3, of alpha acting on ej, theta j. And there you go. So we can obtain coefficients for vector fields or for one forms by acting on the corresponding, or using the corresponding frame or coframe to pick off the coefficients, right? Of course, we might also remember that, you know, you might also recall that before we had that y was equal to a sum j equals 1 to 3 of what? Of y dot ej, right? Ej, because we have the orthonormal expansion at each point because it's a frame, right? So by comparison, we find what? There's a little lemma we can, or part 3 to this proposition, whatever you want to call it. I probably haven't given it a decent name yet, but I'll make it red to make it stand out here. So there's a little lemma, which we'll probably need, which simply states that y dot ej is equal to theta j acting on y. So here he gives you a transference between the dot product of vector fields in the frame and the action of the coframe on the vector field. So that's a wonderful little relation right there. We should remember that. All right. So natural question then. As we think about a frame, the natural thing to think about was the attitude matrix, right? Remember the attitude matrix. It connected the given frame with the Cartesian basis, right? So the question then is, what happens with the attitude basis? How is the attitude basis, the attitude matrix relates to coframe how? Right? So let me just remind you, the attitude matrix, it did what? It related the frame. The relation was EI was equal to A. Oh goodness, I forget. Just a second here. Let me make sure I got the convention right here. Yeah, EI was equal to A I1 E1 plus A I2 E2 plus A I3 E3, like that. Or if you wanted to, you could say more compactly, if you want something just to define the matrix alone, A, the ijth element of the attitude matrix. And Neil used a little a, but I use a big A because I don't know, it's just me. So that would be EI. Oh, goodness gracious. Sad. Not E1s here. Kind of the whole point. U1, U2, U3, right? That's the whole point, is the attitude matrix connects the frame to the Cartesian frame, all right? In some sense, the attitude, like the direction, how the frame is situated, its attitude in R3 is fixed by this. All right, anyway, so U1, U2, U3. So what we really have is Aij is E1 dot Uj. It's a bridge between worlds. It's a bridge between the E frame and the Cartesian frame, right? So there it is. Now, a natural question to ask then is, how is theta j related to, there's got to be some constant, let's say C1, and I really should probably put a j on that, but I'm just going to say well, I guess I could say Cj1 dx, right, plus Cj2 dy plus Cj3 dz. What is this? What are these corresponding sort of quote unquote attitude matrix for the coframe, right? Well, all right. Well, we just learned that if this is a differential one form, right? That we just learned that if alpha is equal to what? It's equal to a sum. J equals 1 to 3 of alpha of Ej acting on theta j, right? Oh man, but that's not what I want. I mean, true, but not what I want. This is for an arbitrary frame, right? What's this look like for the Cartesian frame? So this becomes what? This becomes alpha is equal to a sum. I equals 1 to, well, I could use j. J equals 1 to 3. Oh, j is a bad choice though because I'm using j as a fixed index over there. Let's say I equals 1 to 3. Alpha acting on ui dxi, right? There you go. So as I think about this here, I can see that in view of the previous proposition, I can see that when you take this and you take that and you put them together and you think about it for a second, you can see that C, J, let's see here, I should be equal to theta J, right? Acting on UI. But by the lemma back here, by my lemma, this is equal to UI dot EJ. And with that I will pause because I realize I am in trouble. Alright, UI dot EJ, which of course is the same as EJ dot UI. Wait a minute, that's the attitude matrix. That's exactly AJI. Alright, but so what we have then, let's collect our thoughts here, is theta J is equal to, let me just write it out explicitly, A J1 dx1 plus A J2 dx2 plus A J3 dx3. That, of course, is the sort of attitude matrix relation for the coframe, right? Now, I have a slightly slicker argument, I think, on page 53 to 54 in the notes, but I thought probably would be worthwhile to stumble through it like we just did. So, just to recap in the form of a proposition, if you have frame E1, E2, E3, and theta 1, theta 2, theta 3, the corresponding coframe, then if you can relate the frame to the Cartesian frame by this attitude matrix Aij, good grief, come on, Uj, that's true if you can relate the ith coframe to the same attitude matrix Aij. Alright, so in other words, sorry about that. You could say that the frame and the coframe have the same attitude. Alright, in that sense. Now it's useful, alright, to write the frame and the coframe really in a kind of a nice notation here. So let's talk about some matrix notation for the coframe. Vector of one forms, right? So we just use theta as the column vector, theta 1, theta 2, theta 3, right? That's a column vector of one forms. And also the, oh man, I forget the name of this thing, squiggle. Eventually I'll learn. As the column vector of dx1, dx2, dx3, like so. So we just had this relation that theta I was equal to a sum j equals 1 to 3 of a I j dxj, right? So in this new matrix notation, this just becomes theta is equal to a dc, let's say. All right. And there you go. Well, that's nice, because now we've got the vector of the vector of coframes is equal to the attitude matrix times the vector of differentials, right? In some sense, putting a d here is kind of lopsided. I mean, why does it have to be d here? Why can't you just use c, whatever? I don't know. It's the notation. All right. And that brings us to the structure equations of Cartan, because when we take this notation and pair it to what we already know about the exterior algebra of matrix-valued forms or matrices of forms, depending on your viewpoint, well, that's it. I mean, theorem 2.75. These are structure equations of Cartan, or Cartan structure equations. All right, Cartan structure equations. First of all, 1, d theta I is equal to a sum, j equals 1 to 3, right, of omega ij wedge theta j, where those are the connection forms we talked about before. And 2, the exterior derivative of the connection form d omega ij is equal to a sum over k 1 to 3, right, of omega I k wedge omega kj, right? Now, of course, this we could express in terms of the above notation as what? This is just d theta is equal to omega wedge theta, and this is just d omega is equal to omega wedge omega. Right? In the notation. So let's prove it. The proof will rely on our earlier work with the attitude matrix, right? One of the things we'll need to use for the proof here is we should remember that we had that omega was equal to the exterior derivative of the attitude matrix, right? Wedged with the transpose to the attitude. We proved that in theorem 2.6.7. And we also need to know that the attitude matrix is orthogonal. We proved that before as well. A wedge A transpose, which we could write A transpose, because there are zero forms, matrices of functions, matrices of zero forms, or that's the identity. All right, so thus, if theta is equal to A d squiggle, then that implies what? That implies that d theta is equal to what? It's equal to dA wedge d squiggle. Oh, my squiggles are degenerating. Plus a d squiggle. Of course, d squared is 0, so that's 0. And let's see here. This dA, we can trade for dA wedge A transpose times A d squiggle. Oh, my squiggles are getting worse. But of course, lo and behold, what we have this and this. Well, we know these. This is dA wedge omega A transpose. That's the connection form omega. And ADC, well, that's theta. So we have, and there's a wedgeman here. A wedge theta. And there you go. There's structure equation part 1. Proof of 2. Let's see here, we have to calculate the exterior derivative of omega. And so that's the exterior derivative of dA wedge A transpose, right? Now dA is a 1 form, right? So first, fine, I'll write it out. D of dA wedge A transpose minus, the reason minus is because we're moving D past the 1 form, so our graded Leibniz rule, give us minus there, so dA wedge dA transpose. Alright. Now of course D squared is 0, so I really didn't need to write that down. And we have dA wedge dA transpose. Now, let's see here. Well, remember we had some relations from the last lecture relating dA transpose and dA. Let's see here, I think the one that I want to use is that, I'll write it in orange, dA transpose, right? We can trade dA transpose for minus A transpose dA A transpose. That is an identity that follows from this guy up here that follows. Alright, but so what we have is minus dA wedge minus A transpose dA A transpose, right? But then the minuses go away, you got dA wedge A transpose, parentheses, wedge dA wedge A transpose, putting the wedge in just to make it look all nice and symmetrical. But dA wedge A transpose is omega, so there you go, omega wedge omega. There's 2. Structure equations of a Cartan, simply a consequence of the algebra of matrices of differential forms and the calculus, as well as our definitions of attitude matrix and this new slick notation there. Now, then of course, all this together, we'd like some examples. So let me show you a couple, and then we'll be done. It's actually a pretty short lecture as they go. So some examples of coframes. So my examples are not that imaginative at the moment, but one example that you could look at would be what's it called here? How about this? We have E1 equals to cosine theta U1 plus sine theta U2. E2 equals to minus sine theta U1 plus cosine theta U2. This is not actually in my notes, but I wanted to just point this out because it's kind of an important little thought. So here's the so-called cylindrical frame, right? And we proved that the attitude of the frame was the same as the attitude of the coframe. What that means in practice is that I can just, from this, immediately write down theta 1, right, is cosine theta dx plus sine theta dy, right? And theta 2 is minus sine theta dx plus cosine theta dy. And theta 3 is equal to dz. Now, that said, oftentimes, and here's where it gets a little bit pain, often we wish to express theta 1, theta 2, theta 3 in terms of differentials of the coordinates that we're using. So theta, and of course we got dr, right? And dz, well dz, got that one, good. But the theta 1 and theta 2 a little bit more of a pain. There's a variety of different ways to go at it. For this one, I don't know, how did I do it? How did I do it? I mean, if you want to be rather unclever about it, you can just say, okay, so x is equal to r cosine theta, y is equal to r sine theta, right? So dx is equal to cosine theta dr minus r sine theta d theta, and dy is equal to sine theta dr plus r cosine theta d theta. So, right, then you can just plug those in, and see what happens. Cosine theta dx. And you can see what we're going to be left with is some expression involving dr and d theta, which is what we want. Is this the most efficient way to derive this? Almost certainly not, but it is a way. So we got cosine squared theta plus sine squared theta dr, and then if you look at it, you've got a plus sine cosine, a minus sine cosine times r, and a plus sine cosine times r, so that cancels out, and you're just left with theta 1 as dr. And theta 2, on the other hand, right? Theta 2 is what? Well, let's see here. So we've got minus sine theta dx plus cosine theta dy. Let's see here. How else could I look at this? Oh, fine. I'll be boring. I mean, minus sine theta times cosine theta dr minus r sine theta. Basically, the terms that didn't cancel before are now going to cancel, and the terms that did cancel in the previous step will now not cancel. And so we'll be left with d theta and a product in an r once we write one more step here. So basically this minus sine cosine, so I guess I should say up here, like basically this term and that term cancel. This time this term and that term end up canceling in the products that they're subject to. And so I'm just going to go ahead and skip a step. Sine squared, cosine squared, and there's an r left over, so we get r d theta. So therefore, just to collect our thoughts, theta 1 is equal to dr, theta 2 is equal to r d theta, and theta 3 is equal to dz. That's the coframe for the excuse me, the cylindrical coordinate frame. Now, if you wanted to express the frame also in terms of vector fields of the coordinates, you actually could do this. This is partial r, and this E2 is actually 1 over r partial theta, and theta 3 would actually be, well, that's easy enough, partial z, and it's easy to see why these are coframes, right? The r's, the d theta does not differentiate the 1 over r, it just ends up filling out r over r, which is 1, of course. So that's part of the, if you know what you're going for and you know something about these, then you can probably simplify some of what we're doing here. Anyway, just thought it'd be helpful, maybe, to go through that. 6, but continuing my example from page 5, let me go ahead and, so what we have basically is theta is what? Theta is dr, rd theta dz, right? My attitude matrix is just a 2x2 rotation with a 1 in the other column row. That's zeros for these. Let's see here, cosine theta 1, right? So if I calculate well, of course, you can check that a times theta. Oh, I'm sorry, not a times theta. You can check that a times dx, dy, dz gives you back theta. That's one thing you can check, right? But I think perhaps more interestingly, we could exhibit the structure equations of Cartan. Let's see here, for example, what is d theta? D theta, well, we exterior differentiate component-wise, right? So d theta is kind of boring. It's 0 because d squared is 0. It's 0 because d squared is 0. And it's dr wedge d theta, right? And then that's supposed to be equal to omega wedge theta, right? But what is omega? Well, we worked out before the connection form for the cylindrical coordinate frame is, what was it? It was 0 d theta minus d theta 0, 0, 0, 0, 0, 0. And so that wedged with, what was theta? Oh yes, dr. r d theta dz. Let's see here, so we get, well, notice that d theta wedge d theta is 0, so the thing, and of course 0 times dr and 0 times dz is 0. This next one we get minus d theta wedge dr, and then 0 again. But of course this is equal to 0 dr wedge d theta, 0, which as you can see is exactly d theta, right? You can compare. And then let's see here, what else I wanted to check the other structure equation of Cartan, right? What's d omega here? Well, d omega, well, if this is omega, right? D omega is 0. Excuse me, as d squared theta is 0, so that's right. On the other hand, d omega was supposed to be equal to omega wedge omega, right? Omega wedge omega, well, again, at best we have d theta wedge d theta. That's the only thing non-zero in here, right? So obviously, we get 0. So as you can see, the second structure equation is also true. I mean, it checks, right? So we verified Cartan's equations of structure for the cylindrical frame. All right. Now the same example for the spherical frame takes a little bit more effort. So for the spherical frame, the attitude matrix for the spherical frame is this. It was cosine theta sine phi, sine theta sine phi, cosine phi. Move that down just a little bit. There we go. And then we have, let's see, the next one was cosine theta, cosine phi, sine theta, cosine phi minus sine phi, minus sine theta, cosine theta 0. So that last one corresponds to the theta vector field, same as the cylindrical coordinate frame, right? But this is attitude matrix. It also serves just the same for the coframe to the spherical frame. So we get like theta 1 is equal to cosine theta sine phi dx plus sine theta sine phi dy plus cosine phi dz. We get theta 2 is cosine theta cosine phi dx plus sine theta cosine phi dy, minus sine phi dz. And of course theta 3, we get minus sine theta dx plus cosine theta dy. Now, to convert this, if I want to put this to change to expressions built with rho, phi, and theta, we can use, right, you can use x is equal to rho cosine theta sine phi, y is equal to rho sine theta sine phi, and z is equal to rho cosine phi, you can take the differential of each one of these, plug it back up in here, and when you expand those out, what will you get? Well, let's see here. Actually, I already have that written out. Oops. So, just make a circle here. Let's see here. Take differential, to get dx, dy, dz, and then plug in. You obtain the following. Theta 1 is equal to theta 1, where did I put it? Where'd you go? Sorry, I've lost my theta 1. Oh yes, theta 1 is shockingly d rho. Theta 2 is equal to, as it happens, rho d phi. And theta 3, there's the exciting one, rho sine phi d theta. And so that's how you can obtain these very nice formulas for the spherical frame in terms of the spherical differentials. Obviously, this is nicer to work with than that, right? Attitude matrix gets you started, but it shouldn't be where you finish. I will include the gory and somewhat uninspired calculations which show that in the PDF. I will flash them to you now. Flash. Let me call that 8. Alright. Together with some not the best. Okay. There's that, and then actually the other thing is just this. I'll call that 9. I think these are okay. But I sometimes try to avoid the direct substitution and try to look at other things to see if I can see it through direct calculations like this one I did. Rho squared is x squared plus y squared plus z squared, so like the differential of rho squared is 2 rho d rho, but it's also 2x dy plus 2y dz, 2y dy plus 2z dz. So if I divide this by rho, I get the d rho is like, x over rho dx plus y over rho dy plus z over rho dz. But that's exactly what we have in the spherical from the attitude calculation. That is the theta 1. So that there's sometimes you can do a shortcut like that, something like that. You may or may not be able to see it. Sometimes you have some kind of geometric intuition that helps you shortcut some of this nonsense. Finally, let's take a different look at the structure equations of Cartan. So I wanted to show you how to calculate the connection form from the coframe. Because that's a different angle we could look at this, right? So I just showed you why it's reasonable to suppose this is a spherical coframe. Theta 1 is d rho. Theta 2 is rho d phi. And theta 3 is rho sine phi d theta. So we can calculate d theta 1, 0, d theta 2 is d rho wedge d phi, d theta 3 is, well, that one's more interesting, right? That's it's sine phi d rho wedge d theta plus rho cosine phi d phi wedge d theta. All right, but what do we know? Excuse me. D theta is equal to what? D theta is equal to omega wedge theta, right? But remember, we have omega ij is equal to minus omega ji. So really, when you look at, for example, d theta 1, you just get omega, well, I mean, I guess in principle you get omega 1, 1 wedge theta 1 plus omega 1, 2 wedge theta 2 plus omega 1, 3 wedge theta 3 just by matrix multiplication, but this is 0, and so we just have these two left, right? So, and likewise for d theta 2, but we get omega 2, 1 wedge theta 1 plus omega 2, 3 wedge theta 3, but we can trade that for minus omega 1, 2 wedge theta 1 plus omega 2, 3 wedge theta 3 because of the antisymmetry of the connection form. D theta 3, and I'll just go ahead and put the minus in to start with. So minus d omega 1, 3 wedge theta 1 minus omega, it would be 3, 2, but I switched it around, so 2, 3 wedge theta 2. And the 3, 3 is gone. So we'd like to, our goal is to find, right? We want to find omega 1, 2, omega 1, 3, omega 2, 3. These are unknowns for us. And we want to find it from the information we have here from the exterior derivatives of theta 1, theta 2, theta 3. So let's just go ahead and write down those equations, and I'll try to talk through how to make this calculation. Now, so what do we have? We have, let's see, let's start with the first one. D theta 1 is 0, right? So we got 0, goodness gracious, 0, not theta. 0 is equal to, well, omega 1, 2 wedge theta 2, which was rho d phi. And then we have plus omega 1, 3 wedge theta 3, which was the interesting one, rho sine phi d theta. Alright, so that's equal to 0, right? So let me just talk about that one equation before I do anything else. Either, we have basically two choices here, alright? Choice 1. Choice 1 would be that omega 1, 2 is basically dependent on d phi, and omega 1, 3 is proportional to d theta through some function, multiplication by function. Then you would have like d phi wedge d phi and d theta wedge d theta 0, so you get 0, right? The other choice that you have is that these are canceling. So like this has got a d theta wedge d phi, whereas this has got a d phi wedge d theta, and then they can cancel out and gives you 0. Now if that's the case, you can see then that we'd have to have omega 1, 2 is equal to, well, you got a rho in both, right? But there's the sine phi. We'd need that. So we'd have to have sine phi and d theta. Alright. And then omega 1, 3, in the same token, would have to be, what would it have to be? Well, we already got our rho sine phi by comparison, if this is my choice. So omega 1, 3 would just have to be d phi, I believe. Yeah, and then those would cancel. So those are the two adventures we could choose, all right? That's structure equation, the first one. So this was from d theta 1, all right? Now from d theta 2, what do we get? We have d rho wedge d phi is equal to what? Minus omega 1, 2 wedge theta 1, which was d rho. Plus omega 2, 3 wedge theta 3, which was rho sine phi d theta. All right, let me just kind of box that off here for a second here. So if you look at that, all right, so either I have to have these two cancel, right? So like if omega 1, 2, if omega 1, 2 was d phi, then these two could balance out, right? Because we'd have d phi wedge d rho wedge d rho wedge d phi on the left-hand side, and then we'd have d phi wedge d rho on the right-hand side, but with a minus, so they'd cancel out. But if these guys cancel, then this must be something like with theta. Do I have that over here? Oh, I don't talk about omega 2,3 yet, do I? So I guess I can't decide that. How about the... that would have been omega 1,2 being d phi, so that would be like this option I was just talking about. How about this? Does this option work? Let's think about that one. Maybe we can rule this option out. If omega 1,2's got a d theta in it, right? That means that this can't be canceled out by that. But then this cannot be canceled by that because you've got a theta here, a phi here, and a theta here, so there's no way these could cancel. So aha! So by looking at the boxed equation, this says no. Alright? Can't be the case because it's not going to square with this, given that we already made that choice. Alright, so then d theta 3, hopefully theta 3 doesn't cause us trouble with the theta 2,3 option. So we've got sine phi rather, d rho wedge d theta plus rho cosine phi d phi wedge d theta. That has to be equal to minus omega 1,3 wedge theta 1, but theta 1, remember, was d rho minus omega 2,3 wedge theta 2, but theta 2, remember, was rho d phi. Alright, so to make this work, it looks like, I mean, we have to, you know, we made that choice, right? So omega 1,3 is like some function times d theta, right? And so what can that be then? Some function times d theta. How do I get d theta d rho? Oh, this, right? So I've only got one choice then. It has to have the sine phi in it, right? So omega 1,3 must be equal to match this and that, I have to have sine phi d theta. Alright, and that's consistent with what I said up there too, right? So there's the one. Now to match the other two terms, looking at, let's see here, let me use a different color. To match this guy and this, I need omega 2,3 is what, like, well, the rows kind of cancel out, but you can see omega 2,3 is going to have to be cosine phi, I believe, d theta, yeah. Alright, so in total, we find this. Omega is omega 1,2, so we get 0, we get d phi. Omega 1,3 is, now I'm not saying it's equal to d theta, it's proportional. In fact, the proportionality is sine phi. Sine phi d theta and cosine phi d theta. And then, of course, 0 is on the diagonal and minus what we have down here. So this actually, I mean, the benefit here is not that great, right? Certainly the method of calculation we have from the attitude matrix is sufficient, and nice even, but here, this actually becomes a more useful method of calculation when you're dealing with more abstract frames. For example, in general relativity, if you use a frame-based approach, the so-called tetrad formalism, this allows you to calculate essentially what are Christoffel symbols through a very, very much faster way of calculating actually than direct computation from, say, the metric coefficients and so forth. I don't know how well known that calculation is. It was very surprising to my friend Dipulmoy Guhar Sarkar when he saw it in a relativity class I took. He was astounded by the simplicity of this type of calculations, and he had a couple of years of general relativity classes from the institute in India, so I guess he knows. But anyway, you can check that's consistent with what we found before. So there you go. There's a taste of Cartan structure equations. The matrix